Students, my name is Thirupathi. I am working as assistant professor in Triple department at Marri Laxman Reddy Institute of Technology and Management. Previous class we discussed about half controlled rectifier and full controlled rectifier. Today we are continuing that. So today I will discuss the full controlled rectifier with RLE load. Okay, so we will see here. So here we can observe the main circuit and the waveforms. So first we will discuss about the operation of the circuit. So here we have four switches T1, T2, T3, T4, and these four switches are connected through load RLE. Okay, so here you are observing the waveforms, the source voltage waveform, the output voltage waveform, output current, okay, and other waveforms, source current, the voltage across the thyristors. Okay, so now we will discuss about the operation of the circuit. So you see here, so here it is actually here in the circuit we have a small mistake. So here this is not D2, it is T and it is also thyristor. Okay, so here a small correction. So here actually it is semi-converter. So it is not a semiconductor, it is a full wave converter. So T1, T2, and we have T3 and the T4. Okay, T1, T2 and the T4. So now see, initially the T1 and T3 will be triggered. So initially the T1 and T3 is on. So when T1, T3 is on, then T2 and T4 is off. So when T1, T3 is on, the circuit will be, the current will pass from positive Vs to T1 and T1 to the load RLE, and again it is flow to T3, T3 to minus Vs. So we can observe here from the circuit the Is will flow from T1 to the load, from the load T3 to again supply. Okay, so this is the current direction when the switches T1 and the T3 is on and the T2, T4 is off. So here observe in the output voltage waveform. So here from 0 to alpha we not given any triggered pulse, so output voltage saying 0, so V not equal to 0. So at alpha we given triggered pulse, so when we given triggered pulse then the T1, T3 is on, so we can observe the output from alpha to pi it starts conduction. So here before we studied about the R load and the RL load, there is a small difference between these RL and RLE load is that here we have a battery that is E. So if the output if the conduction is possible, if the output voltage should be greater than the E. If the output voltage is less than V, then at the output waveform we will see it is 0. So it should be greater than the E. So the V naught should be greater than the battery voltage E. So here the output we can observe this line. So this line is the battery voltage E. So if we want the output voltage, then that output voltage should be greater than this battery voltage. Okay, so here from alpha to pi it will be conducts. Okay, so after pi again in the from the supply waveform we will get the negative pulse. So at this negative pulse these T1, T3 will be off. So T1 and T3 is off. Then we will trigger T2 and T4, then it is on. Then T2, T4 is on. So positive cycle, here we have a positive cycle. Positive cycle T1, T3 is on. For negative cycle, T1, T3 is on. Okay, so here again the current direction will be from minus to T2, T2 to load to D2, D2 to again positive. Okay, so here it starts from minus Vs to T2, T2 to the load RLE, RLE to T4 and the T4 to again positive Vs. So this is the current direction of the circuit operation when it is in negative pulse. So we can observe the output waveform. It is also start conduction from pi plus alpha. So at pi plus alpha we will trigger the pulse. So when we given the trigger pulse at pi plus alpha, it starts conduction in the negative region up to 2 pi, up to 2 pi. So here you will get a usual doubt, that is, sir, we have a inductor. So inductor will store the energy. So when the supply voltage becomes 0, that inductor will be act as a source and it will be drive the current in the load, so that here we should get beta extinction angle. Okay, but here we have a freewheeling diode. So when the supply voltage becomes 0, this inductor will be act as a source and it drive the current through the freewheeling diode to the load, so that in the output waveform we will not get any extinction angle. So that is the reason here we are not get any extinction angle. And if you observe here the output current, so we know the inductor will not allow the sudden change of the current, so that the current will slowly increases and slowly it will comes to 0. So before reaching the 0, we will given trigger pulse to the another 2 pair of switches. So that 2 pair of switches will be in start conduction. Again the current rises. Again it's comes try to become to 0. Again it rises. So it will be continue. So the current will be continue in the load, but the voltage will become at some position. Okay. So by observing of this waveform, we can recognize it. And here after that, here we are observing freewheeling diode current. So when it is conduction from alpha to pi, the source voltage is present, so that in the freewheeling diode the current is 0. So when the supply voltage becomes 0, then the inductor will supply the driven the current. So at that time the current through the diode will be present in the output waveform. Okay. So here we can observe the freewheeling diode current, and this is the source current here we are observed, and VT1. So when we not given triggered pulse for the T1 and T3, when we given the trigger pulse of T1 and T3, it is shorted. So when it is shorted across T1 and the T3, the voltage will become 0. So here we can observe it is 0. Okay. So when the negative pulse is present, then this T1 and the T3 will be reversed biased, so that it is turned off. So across these devices we will get a voltage. So we can observe here, that is VT1. In the same manner, another 2 pair of switches that we can observe here. So initially here also the T2 is not triggered. And it is not in conduction, so that across that the voltage is negative minus Vm. And after that we given trigger pulse for T2, so it is conduction. So here it is 0. Okay. So this is the operation of the 3-phase fully controlled rectifier with RLE load, the output waveforms, and the circuit operation. Okay. The next one is, here we are going for the next topic is the 3-phase system. So in this 3-phase system, first we will go across the applications. Okay. So this power electronic subject is a practical subject. So in real times we are using these power electronic converters. So the first one is DC drives. So wherever we have drive circuits, there these power electronic circuits we are going to be used, that especially 3-phase systems. Okay. So used in variable speed drives. So where we have machines, 3-phase induction motors. So in these 3-phase induction motors we have speed control methods. So by using of frequency, by using of voltage, by using of poles. Okay. So by using of different parameters we can control the speed of 3-phase induction motor. So to vary that parameters we are using the 3-phase rectifiers. Okay. And next we are using in the tractions. So tractions also we are going to be using, and UPS systems. So there we required the conversions and induction heatings and electroplating and solar inverters. So in these places we are using the rectifiers and etc. So many other applications also we have. So these are the major applications we are going to be used in the system. And here we have advantages of three-phase full wave control rectifier. The first one is higher and more stability DC output voltage. Why? Because we are using more number of devices, and so that we will get the stable output and lower ripple factors. In three-phase system, we are using more switches, so the switching times is less, so that the ripples are also less. So we will get approximately equal to the DC output waveform, and smaller filtered. So when the ripples are less, obviously we will require smaller rating filters. If ripples are more, then the filter complexity will be increases, the cost of the system also increases. So we will use the smaller filter components. And here we have disadvantages also. So every system suffers with one disadvantage, okay, minimally. So here also we have one, that is higher conduction losses due to use of more thyristors. So here we are using more thyristors, so there is a conduction losses. It's a common thing, okay. So these are the applications, advantages and the disadvantages of the full wave control rectifier. And here we can see the main circuit diagram and the waveforms of the three-phase rectifier. So in the upper part, we can observe 3 thyristors, and the lower part we observe 3 thyristors. So in the upper part, T1, T3 and the T5, so the odd number, and in bottom point we have T6, T4, T2, the even numbers. So this numbering is flexible to analyze the waveforms. So here you can observe the three-phase waveforms. So one is sky blue, one is the red color, and another is the navy blue. So we are represented. The A phase is red, and B phase is the navy blue, and C phase is the sky blue. And here we can observe the load voltages by changing of the firing angles. So here the important point is, if you observe here from 0 to the overlapping point, let us assume this 0 to this overlap point is angle is 30 degrees. Okay, so our A phase will start conduction from these 30 degrees to up to another overlapping point. Okay, so this overall region will be 120 degrees. So if you given trigger pulse between 0 to 30 degrees, it will not turn on. Why? Because at this 0 to 30 degrees, the voltage across the C phase is greater than the voltage across the A phase. So due to that reason, the A phase will not conduct in the region of 0 to 30 degrees, even though you given the triggered pulse. Okay, in the same way, here if you observe here, so at this overriding point B, this A phase will be slowly goes on decreases, and the B phase is goes on increases. So from this point, from this region point, the B is greater than the A phase, so that even though if you are in given triggered pulse also, the A phase will be not conduction. So the operating period of A is from 30 degrees to 120 degrees. Okay, so the overally, if you observe here, the dotted lines are the segregated with the 30 degrees. So here starting initially from the graph, we can observe here the T6, T1. So T6, here we have T6 and the T1. So generally we have an order of T1, T2. So first the T1 will be conduct. So the current path is T1 to T2, T2 to again the C terminal. Okay, the current path. So after that, the T1 will be turned off. So T2 and the T3. So from the T3, T2 and T3 will be in conduction period. Okay. So after that, T3 and the T4, T4 and the T5, and the T5 and the T6, and the lastly T6 and the T1. So this is the pair of switches which are starts conduction for a time period. Okay. So each device, let us assume that T1, the total period of conduction for a phase is 60 degrees. If you observe here, the T1 is conduction for 30 degrees, and after that it is conductor for 30 degrees. So 30 plus 30 is 60 degrees. So if we have to give the triggered after 30 degrees only. So here we are referring 30 degrees is nothing but 0 degrees. It is equals to 0 degrees. Why? Because below 30 degrees, if you give the triggered pulse, it will not start conduction. So after 30 degrees only it starts conduction. So due to that, the 30 degrees reference we will call as 0 degrees. Okay. So here we are varying the pulses. So the second waveform we can observe 30 plus alpha we have fired. After that, load voltage. So slowly we are changing the alpha angle. So we can observe here the different waveforms with varying the firing angle. Okay. So this is the operation of three-phase circuit and its waveform. Okay. And so this is the derivation here. Here we have the average load voltage derivation. So we can observe. So lastly we will get the average load voltage equal to 3 under root 3 VDC. So here we denote as E. So 3 root 3 E by pi cos alpha. And average load current is, we know, ID is equal to V average by R. So that is 3 root 3 EM by pi R into cos pi. Okay. So this is three-phase fully controlled bridge rectifier with resistive load. Okay. So today this session is going to be completed. So thank you very much.